In the rapidly evolving landscape of technology, the concept of responsible machine learning has emerged as a critical imperative. How can we ensure that AI systems are ethical, fair, and trustworthy when deployed in the real world? By embracing this challenge head-on, we pave the way for a future where innovation is synonymous with accountability. Let's delve into the core principles that underpin the development of these imperative systems. Embracing diversity, transparency, and robust governance structures are not just lofty ideals but practical necessities in this journey towards a more responsible AI ecosystem. Let's explore how each of these elements plays a pivotal role in shaping the ethical framework of AI. Ultimately, our collective commitment to responsible machine learning will define the trajectory of technological advancement in a profoundly impactful manner. Why does responsible machine learning matter? As these systems influence critical decisions in finance, healthcare, and justice, the impact on individuals and communities is profound. A biased algorithm can perpetuate inequality, while an opaque model lacks accountability. Privacy breaches expose personal data, risking trust. Responsible ML is about fairness, transparency, privacy, reliability, and principles. In this session, we delve into the 5 pillars of responsible ML to cultivate trustworthy AI systems. Let's navigate the ethical landscape of machine learning together. Welcome to our course roadmap, where we explore the 5 pillars of responsible machine learning. First up, we have fairness and bias, ensuring equitable treatment and avoiding discrimination. Next, explainability dives into understanding and communicating how models reach decisions. Then, privacy protection safeguards sensitive data and individual rights in the ML lifecycle. Model drift comes next, focusing on monitoring and maintaining model performance amidst changing dynamics. Lastly, governance establishes oversight, accountability, and ethical frameworks for ML systems. From fairness to governance, each pillar plays a critical role in shaping responsible ML practices. Remember, responsible ML is about fairness, transparency, and accountability throughout the process. In the realm of machine learning, fairness is paramount. It's about ensuring that algorithms don't unjustly disadvantage certain groups due to characteristics like race, gender, age, or disability. However, achieving fairness is no simple task. It's a multifaceted challenge with conflicting mathematical definitions. The trouble often stems from biased historical data, reflecting societal inequalities that can seep into the models, perpetuating and even amplifying these biases. Even seemingly innocuous features can inadvertently act as stand-ins for protected attributes. Concepts like protected attributes, proxy variables, disparate impact, and treatment, as well as demographic parity versus equalized odds, come into play. Unraveling historical biases embedded in training data is crucial. Fairness in machine learning demands vigilance and a critical eye. In the real world, the COMPAS recidivism algorithm serves as a stark example of failure. This widely used tool, meant to assess criminal risk, was exposed for its significant racial bias. In a ProPublica investigation, it was revealed that Black defendants were falsely labeled as future criminals nearly twice as often as white defendants. Conversely, white defendants were more frequently misjudged as low risk. Despite claims of accuracy by its developers, COMPAS perpetuated racial disparities in the criminal justice system, influencing sentencing and parole decisions and directly impacting individuals' freedom. This case underscores how machine learning systems can reinforce societal biases, leading to tangible harm. It illuminates the crucial necessity of fairness auditing in preventing such injustices. Bias in data can seep into machine learning systems through various channels. Historical bias reflects past discrimination, like redlining. Representation bias emerges when certain groups are overlooked, silencing minority voices. Measurement bias skews labels due to flawed data collection methods, such as sensor errors. Aggregation bias leads to errors by applying a single model to diverse populations, ignoring subgroup nuances. Recognizing these biases is key to constructing fairer systems. So, how can we ensure our data isn't tainted by bias? Ever wondered how a machine learning model arrives at its decisions? That's where explainability comes in. It's the key to understanding and articulating why a model makes a specific prediction, crucial for building trust, debugging, meeting regulatory requirements, and uncovering biases. But the challenge lies in complex models like deep neural networks, which, while accurate, often operate as mysterious black boxes. Unlike simple models where we can easily trace how each feature influences predictions, deep learning networks rely on millions of parameters that can befuddle human interpretation. In this realm, explainability is vital yet elusive. So, how can we crack open this black box? Dive into the world of model explainability with a toolbox of techniques. Feature importance unveils the powerhouse variables shaping predictions. Line delves deep, decoding individual insights with a local lens. SHAP values play the game of features, assigning each a crucial contribution score. And with attention mechanisms, witness the deep learning spotlight on pivotal input areas. Unveiling the hidden gears of models, these techniques shed light on the decision-making process. Ever faced the choice between clarity and accuracy in model selection? In the realm of predictive modeling, we encounter the accuracy-interpretability trade-off. On one side, we have the interpretable models such as linear regression and decision trees, easy to grasp, but they may trade off some accuracy. These models shine in high-stakes scenarios where explainability is key. On the flip side, we have the black box models like deep neural networks and ensembles, offering top-notch performance but challenging full explanation. When deciding between the two, consider the context. Fields like medical diagnosis and loan approvals often demand interpretability for ethical and legal reasons, even if it means embracing a slightly lower accuracy. Choose wisely, as the model's transparency can be as crucial as its predictive power. Amidst the power and promise of machine learning, a crucial pillar stands tall: privacy concerns in ML systems. Think about it, our data, our very essence, flows through these systems, including our most intimate details. Health records, financial particulars, location tracks, behavior patterns, all ripe for exposure. Picture the fallout of a data breach, millions of lives laid bare. And the models themselves, vulnerable to attacks that unveil their training data. Privacy isn't just a buzzword, it's a bedrock human right safeguarded by laws like GDPR and CCPA. Organizations must weave privacy shields into every thread of the ML tapestry, from data inception to model release. The aim? To glean insights while safeguarding individual privacy. In the world of machine learning, protecting privacy isn't just a feature, it's a must. Ever wondered how secure your data really is? Data breaches, model inversion, membership inference, re-identification, these are not just theoretical concepts. Attackers can reconstruct training data, determine if your data was used, and even identify you through supposedly anonymized datasets. It's clear that basic measures aren't enough. We must embed robust privacy techniques into our system architecture. Our data's safety demands more than superficial protection. It requires a proactive, integrated approach that safeguards every piece of information. Let's ensure our systems are fortified against these sophisticated threats. Ever wondered how to protect sensitive data without compromising analysis? Enter privacy-preserving techniques. Differential privacy cleverly disguises individual data points with calibrated noise, safeguarding identities while upholding statistical accuracy. Federated learning revolutionizes model training by operating across decentralized devices, never exposing raw data to a central server. Secure computation breaks boundaries by enabling analysis on encrypted data without ever needing to decrypt sensitive information. In a world of data privacy concerns, these innovative methods offer a secure path forward. Ever wondered why even the most accurate models can lose their edge? Model drift is the culprit. As the world shifts, so does the data, leading to declining accuracy over time. Data drift and concept drift demand vigilant monitoring and timely retraining to uphold model reliability. Stay ahead of the curve by recognizing when your model needs a refresh. Remember, in the world of machine learning, adaptability is key. The COVID-19 pandemic sent shockwaves through industries, causing rapid model drift. Retail forecasts crumbled as panic buying and lockdowns reshaped consumer habits overnight. Credit risk models faltered as employment dynamics and spending behaviors veered from the norm. Transportation predictions became outdated as commuting patterns shifted. This global crisis underscored the urgency of monitoring drift and swiftly retraining models when faced with sudden change. In a world where unpredictability reigns, adaptability is king. In the dynamic realm of machine learning, detecting and managing drift is crucial for maintaining model performance over time. Constant vigilance is key. Monitor metrics like accuracy, precision, recall, and business KPIs in real time to catch deviations. Set alerts to flag performance declines, triggering timely action. Retraining models with fresh data enables adaptation to evolving patterns, ensuring continued efficacy. Before deployment, rigorously validate updated models to safeguard production systems. Success hinges on streamlined monitoring pipelines, swift retraining capabilities, and robust escalation protocols. Some opt for scheduled retraining, while others embrace adaptive strategies triggered by detected drift. Adaptability is paramount in the quest for sustained model excellence. Takeaway: vigilant monitoring and proactive management are essential to uphold model performance amidst evolving data landscapes. Ever wondered how organizations ensure responsible AI? Governance, the unsung hero of ML, provides the rules and oversight. Who greenlights model deployment? How are decisions logged? When things go awry, who steps up? Think model docs, risk checks, approval flows, audits, and incident responses. It's the bridge between tech wizards and business brains, aligning systems with values and laws. So, when it comes to AI, governance is key. Ever wondered what goes into ensuring responsible AI? Think of it as a well-oiled machine with crucial components, model cards, like a model's ID card, detailing its purpose and limitations. Ethics review boards, the ethical compass guiding ML projects. Risk assessment, scanning for biases and potential harms. Audit trails, the paper trail for model decisions and behavior. Incident response, the fire extinguisher for ML system failures. And ongoing monitoring, the vigilant eye ensuring fairness and compliance. Each piece plays a vital role in the governance puzzle, ensuring AI operates ethically and accountably. In the realm of machine learning practices, the distinction between responsible and irresponsible approaches is stark. Responsible practitioners test models extensively across diverse populations, measure fairness metrics, and proactively address biases before deployment. Conversely, irresponsible practices involve deploying models without fairness testing, assuming neutrality without evidence, or disregarding impacts on marginalized groups. Responsible actions include offering clear explanations for high-stakes decisions, documenting limitations, and providing recourse mechanisms. On the flip side, irresponsible behavior entails using opaque models for critical decisions without transparency. Additionally, responsible practices prioritize privacy preservation, minimal data collection, informed consent, and compliance with data protection laws. Irresponsible actions involve excessive data collection without consent, privacy regulation violations, or inadequate data security measures. Remember, in the world of machine learning, responsible choices pave the way for ethical and effective outcomes. As you navigate the world of machine learning, remember these 5 pillars for building responsible ML systems. First, prioritize fairness by actively auditing for bias. Second, demand explainability to comprehend complex models. Third, protect privacy through privacy-preserving techniques. Fourth, monitor for drift to ensure model reliability. And fifth, establish governance structures before deployment. Responsible ML is not a one-time task but a continual commitment. Always question how your AI systems may impact others, strive for fairness, ensure explainability, and safeguard privacy. By staying vigilant and asking the right questions, you can build AI systems that earn public trust. And with building responsible AI requires ongoing vigilance and a commitment to fairness, transparency, and privacy. Think about the ethical implications of machine learning systems in your everyday life. How might responsible ML principles apply to systems you use regularly? Consider the trade-off between accuracy and interpretability in critical decision-making, such as medical treatments. How would you justify investing in fairness auditing and bias mitigation to a non-technical audience? Delve into the privacy concerns of using facial recognition for personalized shopping experiences and propose potential solutions. If faced with a declining fraud detection model, what investigative steps would you take? Engage in discussions with peers. These ethical considerations and critical thinking skills are essential for a successful career in ML. Remember, ongoing dialogue and analysis are key to ethical decision-making in machine learning.